My name is Margit Messmer. I work in the School of Mathematics here at the University of Leeds. In this video, I introduce a few examples involving implicit differentiation, which is a technique very much related to the usual differentiation. I'm assuming that you're familiar with the usual basic differentiation rules. Usually when we talk about differentiation, we think about differentiating a function y equals f of x, and then differentiating it dy by dx, and we get f prime of x. And we know that if the graph of the function looks somewhat like this, then at each point x, the derivative gives the slope of the tangent line to the curve at this point. Now, in general, a curve in the plane is not necessarily always given as a function. When we, for example, look at a very basic curve, the circle, for example, it is not given as a function in x. Although we could, if we wanted, we could write, for example, the upper semicircle here as y equals square root of 1 minus x squared, if this is the unit circle, and the bottom half of this circle would be the negative of this. So we would need to split this curve up into two functions, and it's a square root function which is fairly, not very complicated, but fairly complicated to differentiate. So instead of that, if we take the basic equation of the circle, the unit circle, which is x squared plus y squared equal 1, what we can do is we can just simply differentiate both sides of this equation. That means we apply d by dx to both sides. While doing that, we'll keep in mind that x is our variable, our independent variable if you want, and y is actually a function in x. So we treat these two variables differently as we differentiate here. So if we differentiate the left-hand side here, x squared differentiated gives us 2x. Now, y squared, since y is a function in x, we need to use the chain rule here. So the square function differentiated gives us a 2 times y. And the chain rule says we need to multiply this by the derivative of y, which is a dy by dx. So that's the derivative with respect to x of the left-hand side. The right-hand side is a constant, differentiated gives a 0. So we can here divide this equation by 2 and solve for dy by dx. And what we end up with is that dy by dx is the negative of, is minus x over y, which is a very nice simple description of the derivative in terms of x and y. And it allows us here to plug in, take any point on the circle. We could, for example, take this point here at pi over 4, which has coordinates square root of 2 over 2, square root of 2 over 2. Plug the x coordinate in here, plug the y coordinate in here. Since they are the same, the derivative here is negative 1. That's what we expect, right? The tangent line here has slope negative 1. Now, in this example, as you have seen, it would be possible to consider this curve as the graph of two functions. In general, it is not always possible to solve the equation for y. So we'll see that in some of the examples I'll show you. In this first example, we are looking at the curve with this equation. So the problem we are asked here to do is that we're supposed to find the point in the first quadrant. The first quadrant in the xy plane is this area here, positive and x and positive y coordinate. And we're looking at this curve, and we're looking for the point which has a horizontal tangent line. Now, to plot the curve of this equation, that's not very easy to see right away what the curve looks like. So we are going to use an online curve plotter to see what this curve looks like. To plot this curve, I'm using an online implicit curve plotter. that's publicly available, and I encourage you to access that site. The address is pasted on this website, and you can pretty much type in any equation involving x and y, specify the range over which this curve should be plotted, and it will give you the picture. So I've pasted in here the equation we just looked at, and we look at the graph, and you see that it is a nice figure 8. Also, it looks like the infinity sign that we use in mathematics quite frequently. Now, if you look at the picture, the point we are looking for is this point here in the first quadrant, with which has a horizontal tangent line. Let's just, before we go back to the equation, let's just roughly see what the coordinates of this point, what the coordinates of this point are, so that we can check our answer later. So the x-coordinate of this point is roughly 0.7, something like this, and the y-coordinate is roughly 0.3, I would say. So let's keep that in mind, and when we do the computation, see whether that actually comes out at the end. So a horizontal tangent line means that we looking for dy by dx equal to 0. So we'll take our equation, I'll just copy it here again, x squared plus y squared squared equals to x squared minus y squared. We apply d by dx to both sides. So we apply d by dx to both sides as before. The left-hand side is a composite function, so we need to use the chain rule here. We differentiate the square here first, get 2 times x squared plus y squared, and multiply it by the derivative of what's inside the brackets, which is 2x plus, now the y squared, again, we need to think of y as a function in x, and as before, use the chain rule and get as the derivative 2y times dy by dx. That's the derivative of what's inside here. On the right-hand side, we'll get 2x, and again, treating y as a function in x, we get 2y dy by dx. Now, instead of solving this equation for dy by dx, I will right away set dy by dx equal to 0, because that's what we need. And we'll have these terms going away here, and we are left with, I can at the same time divide the equation by 2 on both sides. That makes this 2 go away, and these 2's go away, so we are left with x squared plus y squared. Since dy by dx is 0, we are left with a 2x here, and on the right-hand side we are just left with x. Now I can divide here by 2x, and the x will go away since I know that x is non-zero. I'm looking for positive x. And we'll get x squared plus y squared is equal to 1/2. And you will notice that this is nothing else than the equation of a circle with radius square root of 1/2. So let's look at our picture. So our original curve is the figure 8, which we saw on the screen. This is the point 1. And now the condition that the tangent line is horizontal gave us the condition that the point needs to lie on the circle with this equation. So as I said, this is the circle with radius square root of 1/2, which is square root of 2 over 2, which is roughly 0.7. So the circle we are talking about is this one. And you see the point we are looking for is the intersection point of these two curves. That's where our original curve, the figure 8, has a horizontal tangent line. So we need to find the point which satisfies both of these equations, this one and this one. So we can just take this equation and replace the term x squared plus y squared in here by 1/2. So we'll get that 1/2 squared must be equal to x squared minus y squared. So this tells us that x squared minus y squared must be equal to a quarter. So I have these two equations here, and I need to solve them for x or for y. If I add them together at the left-hand side and at the right-hand sides, the y's go away, and I will get 2x squared equals to half plus a quarter, that's 3/4. So we have that x squared is 3/8, and therefore x must be plus or minus the square root of 3/8. But since we are looking for the point in the first quadrant, we are looking for the positive root here. So that's the square root of 3/8, which is, since this is 6/16, so we have that this is the square root of 6/4. Square root of 6/4 is roughly 0.61. And since we are asked to give the point, so we need to give the x-coordinate as well as the y-coordinate, we'll compute y. Let's use here this equation here. So y squared is equal to x squared minus a fourth. X squared is equal to 3/8 and minus a fourth. That gives 1/8, and so y is equal the square root of 1/8. And we can fill that its square root of 1/8 is the square root of 2/4, and that's our point. So let's just think back of when we looked at the picture. So the x-coordinate is about 0.61. Square root of 2/4 is about 0.35. So that roughly corresponds to what we expected when looking at the picture. So we've identified here this point with the horizontal tangent line.